Hello, this next video in a playlist that I'm calling Complex Variables, where we're going to do a playlist on complex analysis. First, we're going to look at complex numbers, and so today's topic is the complex quadratic equation with complex coefficients. So a quadratic equation can be defined as this. We have A, B, C, and Z complex numbers, A not equal to 0. Then a polynomial of degree 2 is called a quadratic equation, and this is it. P of Z is AZ squared plus BC plus C. Now the goal is to drive the quadratic equation slash formula for Z that is a 0 of the quadratic equation. So we want to find the Z's that make this, when you plug it in, you get 0. Now before we start, we want to look at the square root of a complex number. Now I have a video earlier in this playlist called Roots of a Complex Number where we look at this in general, but we didn't give the specific example of the square root or raised to the 1/2 power. So I want to do that just so there's no ambiguity. So let Z be a complex number. The square root of Z is this. So the square root of Z is Z to the 1/2. So you write it in polar form, take it to the 1/2. Then it says you take the 1/2 into the modulus, but then you add integer multiple of 2 pi and then divide by 2. And these are both of the roots of Z. So it's the square roots of Z. Now, when K is 0, then you plug in 0 and you get this number. Plug in 1 and you get this number. But we can simplify it, right? Plug in 1, the 2's cancel. We can distribute the I and then take the exponent and split it into 2, the multiplication of the exponentials. But e to the I pi is -1. That's Euler's formula, so it can come out front. And these are the two roots, or the values on each Riemann surface, if you want to think about that, and we'll cover that in probably 20 videos. But really it's plus or minus this value, whatever the root is. And see, this is very analogous to the square root in the real number system. So the square root of 3 is plus or minus 6, right? 6 times 6 is 36. Minus 6 times minus 6 is 36. Now let's derive the quadratic equation or formula for Z. So let's find the zeros of Z. So we start out with the polynomial set it equal to 0, and we want to find the Z that makes this happen. So we divide every term by A to sort of isolate the Z squared by itself. We subtract the C over A to the other side, and then we add a well-chosen 0. And now you might look at this, you're like, no, you just added B squared over 4A squared to each side. Well, that's the same as adding a 0. If you think of subtracting this to the other side, then we add and subtract the same thing, which is 0. So this is adding a well-chosen 0. But the left side becomes a squared term when you factor it, and we combine the fraction on the right. Now we take the square root of both sides, and that's where the plus or minus comes into whatever this square root value equals. Subtract b over 2a to the other side, combine like terms, right? The square root of the numerator square root of the denominator is 2a, so it can come out, and when we combine the fractions, we get this. And it looks exactly like the formula for, when we're dealing with the real number line. So let's go through 3 examples and call it quits for the video. So Z squared minus 2Z plus 2, we use this formula. Then it's minus B squared minus 4 times A times C. A is 1, B is 2, all over 2A. Do the math, you get minus 4. The 4 can come out as a 2, and then the square root of I is square root of 1, square root of minus 1 is I. The 2's cancel and we get this. Now here's a big note. Note that the solutions are conjugates of each other. They're complex conjugates. And this is always the case when the coefficients are real. And we'll prove this in a later video. So notice it's a 1, a minus 2, and a 2. Those are real coefficients. And so we get the solutions come in conjugate pairs. Now let's look at a second example. 3, 5i minus 2. So The coefficients are not real. It's a complex coefficient, but we can still use this formula. So it's minus b squared minus 4 times a times c all over 2a. So the 2 distributes, so we get 25 times I squared. I squared is minus 1, so minus 25 plus 24 is minus 1. Square root of minus 1 is I. Then, which is this, and then we can look at each case or each value on the Riemann surface is this. So now let's do a third example, a little more difficult. Z plus 2i minus 2i z plus or minus 7 plus 26i. So here we have complex coefficients. Well, but we use the same formula. So minus b plus or minus b squared. Now notice it's a minus for a c, but this c is a minus, so I cancel and make it a plus all over 2a. Well, when you do the math of this inside, so you take the square of this and combine it with this complex number, you get 28 plus 96i, right? And so this is the answer. You could leave it in this form, but let's actually find what the square root of 28 plus 96i is. So we have to convert 28 plus 96i to polar form to take a square root, because it's much easier. There's theorem, de Moivre's theorem helps us find it exactly. So see previous video in the complex variable playlist for this. First, let's find the modulus of 28 plus 96i. So, and we're going to denote it by r. So r is the modulus of this, which it's the square root of the square of each, the real and then the imaginary component, which is 100. So that's 100. That's r. So next, find the argument, which is the angle that the complex number or the vector creates with the real axis. And it's as in a previous video, the angle, the argument, is the arctan of the imaginary divided by the real. So it's the arctangent, which is the inverse tangent. I just think when it's a minus 1, I'm not, anyway, it's the arctangent 24 over 7. So then the 2 square roots of this number 2896i is this. So remember, in complex form polar form is this. So the modulus is 100, but we're taking the square root of it, so that's what this square root is. And according to de Moivre's theorem, we take the angle divided by 2 because it's the square root. So, raised to the 1/2 power, that's the 2 that gets there. And this theta is still this arctangent of 24. So we use a calculator to find the cosine of theta over 2, which is a cosine of the arctangent over 24 over 7 divided by 2, which is 0.788. And then we also use a calculator to find the sine of theta over 2, and it's 0.615. Hence, the square root of 28 plus 96i is plus or minus, right, taking the square root of 10, which is the square root of 100. And then this piece is that, this piece is here. And then multiply the 10 in, we get this. Now we have to plug that back into the first equation, right? So this was the solution of our quadratic equation. But now we have something explicit for that square root, which is this. Now we can combine the real terms and the imaginary terms, divide each by 2, and we get this. But now let's go ahead and divide each term by 2, and we get this. Okay, well, that's all I have for this video. The next video will be on complex polynomials with degree n. So hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.